In this section, we're going to begin talking about exponential functions. Now, they are functions that have a base or something that is raised to an exponent. We call that base b. And the exponent is the variable. In other words, the unknown value is going to be in the exponent, which makes them interesting to look at. And one thing we have to keep in mind is that this value, this base number, is always greater than 0, but it's not equal to 1. And it's any real number, okay? As far as x goes, that can be any real number. I'm going to take a couple of them and look at them, and especially using your graphing calculator to examine what these are going to do as functions. So the first one we see is we're letting this function be defined for us. F of x is equal to 3 to the power of x. So when they ask us what f of 3 is, we say, well, that's equal to 3 raised to, and all we do is replace the x with our 3. And you can see 3 raised to the power of 3 is fairly easy for us to solve, isn't it? It's not really anything but just a simple value, and that would be the value 27. Let's look at another one. If I said f of negative 2, and I'm going to replace it in my function here, it would be 3 raised to the power of negative 2. Now, raising something to a negative exponent means it becomes a fraction. To get rid of the negative exponent, we take this 3 to the bottom of our fraction, and we say, okay, now it's a positive 2, and there's nothing else to put up there but a 1. We have to put that to keep our fraction placeholder. And so we say this is 1 over 9, isn't it? So that would actually be 1/9. Let's take in our function and now replace the value of x with a fraction. So this is going to look a little strange to us. It's going to be 3 raised to the power of 3 over 2. Now this is just remembering some of your algebraic principles because we'll have to use them in this section. Now when I say that this is 3 raised to the power of 2, I'm really going to turn this into a radical. I'm going to look at it and say, I really want this to be the square root, because that's what that tells me, the square root of 3 cubed. Okay, that helps me a little bit. And I could have, of course, put that cubed outside of the radical, but it serves my purposes to do it inside this time. So I say, okay, 3 cubed is 27. So this is really the square root of 27. And when I look at 27, I realize there's a perfect square inside 27 because this would factor, and I'm going really slow here because you're going to have to brush up on these skills. And this is going to factor into 9 times 3, and I can take the square root of 9 out as a 3. So what I end up with is 3 times the square root of 3. Now, that's not the notation I want. I want it to have a fractional exponent is what I really want it to have. So I'm going to look at what this is, and I've got 3 times 3 to the power of 1/2, right? Well, that's still not good enough. So what is 3 to the power of 1? Could I express that as halves? I would just say that's 3 to the 2/2. Okay, now I've got them in the same fractional type of fraction here. And when I multiply same base with exponents, I add the exponents, and I can add these because they have common denominators. So I say this is 3 to the 3/2, isn't it? And that's how I would leave my answer. This is really 3 to the 3/2. That's how I got it. All right, let's look at what we have when we have a decimal. Well, really, this is not too difficult for us to see. We would just replace our x with 5.26, and then it's probably going to be time to go to your calculator and see what it gives you for that. I'm going to say this is 3, and I'm going to put my little arrow there, or my little caret sign, you know where this one is, that says raise it to a power, and the power is 5.26. And then I'm going to resolve that, and I get 323 let's just go to 3 decimals, 339. So this is going to be approximately 323.339. If I wanted it exactly, I would have to leave it in this exponential form, but approximately I can get it to a decimal. Now, what about pi? And you haven't used pi before, and you know it's a never-ending it's a never-ending decimal. And so where do you find it on your calculator? Look right above this little up arrow sign, the one we use to insert the exponents. And if I want to see what pi is, I just say second, and I hit that arrow, and it inserts pi, and then I can just hit enter, and it evaluates pi for me. It's 3.15 I'm sorry, 3.141592654, and it goes on, it never ends. So that's the value of pi. So now you see how I can insert it here in my function. I'm going to say, well, this is really 3 raised to the value, to the exponent pi. And I would put in my 3, and I would do my little caret sign, or my little up arrow sign, and then I'm going to put in second and hit that arrow again to insert pi. And when I hit enter, I get 31 point, let's go to 3 decimals, 544. That's it approximately. So it's approximately 31.544. And like I said, to be exact, I would have to leave it in exponential form, 3 to the power of pi. Now, we've got some parent graphs that we need to look at and we need to memorize for exponential functions. And the first one is going to be if b is greater than 1. Now remember, b can't not, the base of this thing cannot be 1. It doesn't really give us the function we need. So we're going to need b is greater than 1 for this one. And if it is greater than 1, we will see certain things always happen. Now these things always happen if b is greater than 1 or b is between 0 and 1. Now b can be any positive number. It's not going to be negative, but it can be a fraction. As long as it's not 1, it can be between 0 and 1. So we could have, the base of 1/2 or the base of 0.25 or whatever. So let's look at what always happens. These 3 things you should always be able to find with these exponential functions. There's always going to be the 0.01. That point is sort of given to us. It's going to be there in the parent functions, okay? So in these base functions, and then we're always going to have the 0.1, and the y portion of it will be whatever the base is. B will be the y. And the third thing we're going to always have is for -1, we're always going to have the fraction 1 divided by b. So those things we sort of know. And if you look at them here, I can show you. This is 0, 1 is always here, and this is the one where b is greater, the base is greater than 1. And of course, when the base is not, when it's a fraction, it's going to sort of reverse itself. We call this one an increasing function because it's increasing as it goes toward the right. It goes up, and we call this one, of course, the other thing is the decreasing, because as it goes toward the right, it's going to go down. For both of them, you have a horizontal asymptote. Not really a vertical one, but we do have the horizontal asymptote at x equals 0. These are the 2 parent functions that I'm putting in, okay? Look at what we've got. We've got 0, 1 in both of them. We've got 1 divided by b, and we usually look at this as the parent function being 2x, okay? 2 to the power of x. And so this one would be equal to 1/2 to the power of x. Good examples for us to look at. And so we say this one, I have y is equal to 1 over b, and so y was going to be equal to 2, 1 over 2, right? 1, 2, I'm sorry, I'm getting my terms mixed up. And the next one I've got, what is this other point going to be? Well, it's going to be 1, 1/2, isn't it? And I would find a third point on my graph using my calculator when you get your function in. But this one really helps you to graph it. The next point that's going to be a whole number is going to go way up here. Now, let's take our graphing calculator and let's see if we can enter some of these using it. And look at these 2 particular functions, these 2 particular, what I'm going to call parent functions, okay? So the first one is going to be, and I'm just gone to y is equal to, and the first one is going to, of course, be 2 to the power of x. So I enter a 2. I want to put the exponent of x, and so that's my first one. And the second one, the base is 1/2. So I'm going to enter the base of 1 divided by 2, and I'm putting it in parentheses just so my calculator doesn't get confused at all. And I say raised to the power of x again. So I've got 2 to the power of x, and I've got 1/2 to the power of x. The first one is going to be blue in mine, and the second one is going to be red. And let's look at what the graphs look like. Now, you can see it looks like perfect images like I've drawn here for you. But the nice thing about graphing them is not really to see the graph as much as it's to see the table of values. So instead of having to plug points into these particular functions and solve, I'm just going to go to my table, and I'm going to be able to see that I have the 0.01 is in both of them. You see it? It's 0, 1 is in my blue graph, the first one, and it's 0, 1 is in my red graph, my second one. And then I can see that I've got negative 1.5. That would be a point that I was interested in. And, and for that one, negative 1 ended up being 2 here. So you can go and easily put the points that you need to draw your functions, okay? And that's kind of what the purpose of using your graphing calculator will really help you as you're going into this section. On this page, on page 2, we've really got the rules that I just told you and comparing the parent functions, the parent graphs for exponential functions. And it's looking at it with x, of course, equal to the value of 2. And what I'm trying to show you in this one is that for both of them, both the one that is a whole number and the one that is a fraction, we have a horizontal asymptote. Excuse me. It is the x-axis. It's where y is equal to 0. And this is an important point. We don't really have a vertical, but we do have a horizontal asymptote, and we need to keep that in mind with these functions, especially when we're going to be doing some transformations with them. So there's your notes one more time for you if you want that page as reference. Now let's go down and let's look at a couple of what we'll call parent graphs, but this time what we're going to have for that base is the base is going to be 5 and 1 over 5, okay? So when the base is 5, I know I'm going to have, and I should keep this in mind, that I'm going to have an increasing graph. It's going to go up to the right, and I know certain things about it. I know that first point, I'll write it down here. I need at least 3 points to graph it. I know that it's going to have the point 0, 1 in it. Oops, 0, 1. So that one is a given. And then the second thing I know is that it's always going to have the point 1, comma b. Well, the base is 5, so it's going to have, this one's going to have the point 1, 5. And then I know it's going to have the point negative 1, and this one is going to be 1 over b. So 1 over 5 is, of course, 1/5. So I can fairly easily graph that without the calculator if I know those rules. So I'm going to say I have the point 0, 1. It's always going to be in here. And then I have the point 1, 5, right about here. And then I have the point negative 1, 1/5, which is really close to the asymptote, isn't it? So if I draw it, getting as close to that asymptote as I can, and it's going to go up quickly to the right, this would be my function graphed. And you can put it in your calculator, but if you know those 3 points, then this is what we call a parent function, because there's nothing else to it except for the base and the exponent of x. Another one, base is a fraction this time, and the exponent of x. So this time I know, since that base is a fraction, it's going to be a decreasing function. In other words, it's going to come way up. It's going to rise quickly up here to the left, isn't it? But I do know certain points. I know it's going to have the point 0, 1. And then the same rules apply. I know it's going to have the point 1, comma b. Well, the base this time is 1 over 5. And then I know that it's going to have the point negative 1, 1 over b. Now that might be a little bit trickier for you because you're thinking, well, b is the fraction already, but that's 1 over 1/5, which is the same as 1 times 5 over 1, isn't it? Which is 5. Okay, don't be afraid to write this out until you're sure of it, okay? So I've got 0, 1 right here. I've got 1, 1/5. This time that's where it's going down toward that horizontal asymptote, isn't it? And then I've got negative 1, 5. It is the exact opposite of what I just drew with my first function. Now I'm trying to make it go through these points and not touch that horizontal asymptote, but you get the picture. It gets really close to it, but doesn't touch it. Now on page 3, let's look at your transformation rules involving exponential functions. And they're going to be really familiar to you. They're going to be basically the same rules we've been following up until now when we've been transforming our functions. But look at this. What you really want to keep in mind is that if you have a plus or a minus at the very end of your function, it's going to shift either upwards or downwards. That one is easy for us to understand. Now, what about the right and left shift? Well, that happens as part of the exponent. So if the exponent has a number added or subtracted, if it has it added, it's going to shift to the left, subtracted shifts to the right. That's the one that seems backwards to us, but it's pretty familiar. That's the right and left shift. The next ones are going to be reflection. Now, where do we see that it reflects about the x-axis? That's if the negative is right there next to the equal sign. About the y-axis, the negative has to become a part of the exponent. And the hard one is going to be these vertical and horizontal stretches and compresses, okay? Stretches and shrinks. So what we have is that if we have a number that's been multiplied times, if it's in front, if it's right up here in front next to the equal sign, then it's going to be a vertical stretch or a vertical shift, shrink. And if it's added to the exponent up here, a coefficient added to the exponent, then it's going to be a horizontal. Now these mostly you're going to use your graphing calculator to help you find the points for. These others you should be very easily able to shift the graph around without doing anything. Now I've changed this page a little bit since yours was printed, so take a look and see. I've added a graph to the bottom of mine, a blank graph, and I've changed this from a -5 to the x plus 3 to a -2 to the x plus 3. The first thing I want you to look at is to see that this particular graph that has been added here is the parent function. And the parent function is, we'll call it p of x again, I guess. P of x here is equal to 2 to the power of x. That's it, okay? Parent function, and you can see how it follows the rules, and it goes through 0, 1, it goes through -1, 1/2, and it goes through 1, 2. That's the parent function for 2 to the power of x. So how would I transform it? What would my transformation rule say it had to do? Well, first of all, this negative out in front is going to say it reflects. And where it's going to reflect this time, if you look at the negative in front, it's going to reflect around the x-axis. It's an x-axis reflection. So it's going to flip from pointing up here to pointing down. So I can sort of see that in my head. This top part would just kind of flip over and turn down. Now, what else is going to happen? Well, up here, I've got +3 added to the exponent. And that is where it tells me to go left 3 points, 3 places. And then the final one is the easy one, down 2. Now, there's no compressor or there's no compression or shrinking or compression or stretching in this one. Because it stays the same as what we have our parent function. So once I have my parent, I can easily go ahead and graph this one. But you might want to just plug some points or plug these into your graphing calculator and kind of look at what it does. And if I'm flipping this around, I flip this most important point, and the most important point on my graphs is always going to be this one, 0, 1, okay? Find it first, and then start working with it from there. If I shift it down, it goes to here, doesn't it? So that's the reflection. And then if I go left 3, it comes there. And if I take it down 2, that is my new, I'll put it as my new 0, 1, okay? That's where 0, 1 went, was there. It went to -3, -3. All right, now from that, I should be able to kind of tell what this graph is going to do. One thing I do know, this when it says down 2, my asymptote, my horizontal asymptote, went down 2. So I'll take a minute now to just kind of draw that in. I'm going to draw it in with a dotted line right here on the second graph I've given you. You can work on the first graph if you want to. You might want to just have another color of ink when you're working on it. And we took the first point that was here, that was 0, 1, and we said, well, that one became -3, -3, didn't it? Oh, sorry, I took it down to, should have gone down 2, and instead I went down 3. Ignore that and draw the line here. So this one becomes -3, -3 right here. Okay, now what's the next point? Well, let's take a look at what this looks like in our graphing calculator, shall we? I'm going to go up to y is equal to, and I'm going to just put in this new function. I'm going to say -2, and note, don't use the minus sign in front of it. It'll, of course, give you an error. When you're saying a negative in front of a number, this is your key for that. So I say -2, and I say it has to go to the power of, and then I'm going to say x plus 3. And then I need to get out of that exponent and say -3. And I can use the minus sign for that one because it's not leading the number, okay? It's not the first thing in my equation. Now I'm going to graph. And what I thought was going to happen did in fact happen. it turned upside down. It starts going down, doesn't it? It turns upside down, it flipped around, but the most important thing I need is these points, right? Because I don't want to plug these numbers in. I could plug in a 0 for x, I could plug in a 3 for x and solve this, but the calculator's already done all that work for me. So what points do I see that I might want to graph? Well, I see -1, -6. -1, -6 looks fairly easy. There's one. Look, -3 is there, and that was, of course, my original most important point. Moved to that, so I'm glad I found it. -2, -4 is one other point that I could find. And then as it gets closer and closer to this horizontal asymptote, you know, it's going to get further and further negative. You can see it just kind of gets closer and closer to it, but doesn't ever get all the way up to that -2, right? So I know my horizontal asymptote of x is equal to -2, y is equal to -2 is correct. All right, so let's graph it as best we can. Did I have another point? I wanted another point. Hang on a minute. I was trying to get one that was actually on my graph. When I get to 0, I've got the -10, but that's good enough. That'll at least be on the paper. The others go quickly. It goes quickly down. So I can't find them, but this is what my graph now looks like, which I pretty much found with transformations. Now on this page, we want to talk about the natural base, which is e, which is really an irrational number. It's called the natural base, where e always approaches a number, but it never really gets there. It's got a never-ending decimal, just like pi does. And it was really discovered when people were studying compounding interest. They were trying to calculate compounding interest, and they discovered this never-ending decimal of e. And we have found it so useful for so many things that we now you have a calculator function that has e in it, and you should be able on your calculator to find that number. And on mine, you can see e to the power of x is right over the natural log number ln, that feature, and we'll talk about that in a minute. And you should be able to insert e from your calculator. So take a minute and find it. If I'm looking for just the value e, then I find it right here over the division symbol. I don't know if you can see that or not, but if I wanted to just insert it, let me get out of what I'm in here, then all I would do is say second and hit the division button, and it would insert e. Now if I want to know the value for e, I can hit enter and it tells me, and of course it's got never-ending decimals going on, but that's basically what that natural base is. Now, when we look at it as a function, we look at it as the parent function, f of x is equal to e to the power of x. And it graphs very, very much like our other parent functions. If you put the value 0, 1, you'll find it on the parent function, and there it is. And the other thing is, I said, one of the other points was -1, and it would be, e to the power of -1 here, which is really 1 over e, isn't it? And so that's what they've got, this point here. And then the next one I've got is of course 1 over 1 comma e, okay? So, all you have to do is go back to this sheet and these 4 points or 3 points that we were able to graph very easily, and you can find those. But that follows through for this particular exponential function also. Now, why do we use it? Well, there's a really good example here. And it talks about the gray wolf population of the Western Great Lakes. And so they've been watching it and watching what it has been doing there for a while now. And they found that it's following a path. And this is the path that it's following. It follows this exponential function. And it says that f of x is equal to 1145 times e to the power of 0.0325. And there's our x, our unknown. And where x is in this particular function, the number of years after the year 1978. So what they want to know is, what is the projected population in this recovery area in the year 2017? Well, to find x, we got to find out how many years 2017 is after 1978. So I take 217, of course, and I subtract 1978. and I find out that that's 39 years. So that's going to be what I'm going to have as x. So I'm going to say f of 39 is what I'm interested in for this particular function, and I'll say it's 1145 times e, and it's to the power of 0.0325 times 39. You can multiply it out early if you want to and get that exponent. And sometimes with your calculator, that's a good idea, is to do this multiplication out early and then just raise it to that particular exponent. However, I think I can do it. I think I might be able to demonstrate it with just raising it to that power and using some parentheses around it. So let's see what we get. I get 1145. And then I'm going to say times e, so I have to insert my e, which is over here above the division. So I say times e. And then I want to go to the power of. And I'm going to put these in parentheses because I want to make sure it multiplies that exponent first. Sometimes it's a problem in calculators. 0.0325 times, and I'll say 39, and close parentheses. So I think I can do it like this. Let's just see what that value comes out to be. And what I get is 4,066.995. And I would probably say, well, I'm not going to project that 1/100th of a wolf that maybe not born yet. So I'm going to say my value here is going to be approximately 4,066. And that is 39 years after 1978. Now I've added a page into your guided notes. This may be an extra page. If you don't have it, you can, of course, make notes, write this out on a sheet of paper, but I just want to go over a couple of things one more time because they can be confusing. One is what happens if we have a negative in our exponent. And I think we went over this one time, but let's just say if the function is g of w, and the function is g of w is equal to 7 to the power of w, and they want us to find g of negative 4. So you would say then that g of negative 4, let's see if I can get this page to settle down, g of negative 4 is equal to 7 to the power of negative 4. Now, of course, that turns this into a fraction with the denominator 7 to the power 4, and then you just take your calculator and you'd say 7 to the power 4. Well, that's 2,401, and so that is my answer for that one. Now let's take a look at if I have an e, if I have the function e. I'm using e here. So what is it if f is to the power? I'm looking for f of 2. I'm looking for the function of 2, and I would still keep my e. But as x, I'm just going to replace the x and the 2 is what I'm trying to say. And this is actually e to the power of 5, and you can easily put that in your calculator. Now, this is what we call the exact answer, okay? If you need an exact answer and it has e in it, you really can't resolve it. You're going to have to just leave it e to the power of the exponent. But if you want to approximate it, then you can say, well, go ahead and say e to the power of 5. And when I put that into my calculator, I'll do it real quick. I would say enter the e first, and the e is above the division symbol, remember? So e, and then I'm going to say an exponent, and that exponent is going to be 5. And then, of course, when I hit that, it's going to evaluate it, and it's never going to have that decimal's never going to end. So it's approximately 148 point, let's just go to 3 decimals and say it's 0.413. So you have an exact answer and you have an approximated answer when it's involving the number e. Now let's look at this one and see if we can graph them. And really, I want you to pay attention to transformations here. So I'm going to come down and say, well, the parent graph of this one would be, and I'll call it p of x just to give them something different. I'll say the parent graph would be 2 to the power of x, right? I'm going to get rid of the negative 5. I'm going to get rid of the plus 3, and I'm going to say that's my basic parent graph. Now, if I want to put the parent graph on there, I know that the horizontal asymptote is right here. It's y is equal to 0. So y is equal to 0 is my horizontal asymptote for the parent graph. And then I know the points on this thing. I know I can come up with them real quick. I know it has 0, 1, and it has -1, 1/2, because it would be 1 over the base of 2. And then it would have the second point would be 1, and it would be the y value is going to be the base, which is 2. So here I am with this perfect parent graph that I didn't really have to do too much to, but I can plug it into my calculator and get some more points to make it even better. Let's do y is equal to, and over here we'll say 2 to the power of x. And there's my parent graph. Let's see what it looks like. That's not going to help me much, but it does help me when I go to the table. So I've got a couple more points. I've got 2, 4. That's useful. And then I've got, what do I have? 3, 8. And however many you want to make yourself comfortable drawing it is fine, but at least 3. And then I know it goes really, really close to the asymptote, and it's going to rise quickly. I know that this is an increasing graph. Okay, and I know certain things about it. Now, I'm going to go ahead and say, what's the domain of this one? Well, the domain for the parent is going to be -infinity to +infinity. And the range for this parent graph is the real issue, because the range is going to stop down there at that horizontal asymptote. In other words, it will approach 0 on the bottom, but it'll never reach it. So I'll use this parentheses to show that it's bounded by 0, but it's not reaching 0. And how far up does it go? +infinity. So that's parent information for you. Now, what about my new graph? Well, if I want the new one, I can say this is going to say, go to the right 5. And this +3 is telling me to go up 3. Now, the up 3 really helps me as far as putting in my horizontal asymptote, and I'm going to try and use a different color pen here. I went from a y is equal to 0 to a y is equal to 3, and here it is. See if I can draw it in the right place this time. So there's my new horizontal asymptote, is y is equal to 3. I can draw it, but I can't write it. Okay, now what happens with the other points? Well, I'm going to take care of the up 3, and then I've got to go right 5. And here's that most important point. Remember this one? That most important point, that 0, 1. If it goes up 3, 1, 2, 3, and to the right 5, it goes 1, 2, 3, 4, 5. This is where it ends up. So I took it and went up 3, and I went right 5, and I ended up right there. Isn't that +5, 4, something like that? Should be anyway. Now I can do the same thing with these other points that I've graphed. I can go, but this one's a fraction, so it's a little difficult. And if I did a compression, if I had a compression or something in here, I would really need my calculator to tell me where these other points are. So let's just use the calculator and see if we can find some more points. I'm going to go to y is equal again, and I'll just leave that one as the blue one and come down here and make my new one red. And it's going to say 2 to the power of, and I'll say x minus 5. And then I need to get out of the exponent and say +3. So 2 to the power of x minus 5 plus 3 is my second graph. And when I look at it, I can tell what it's going to do. Yep, it does look like it went up 3 and to the right 5, doesn't it? Using my table, I can find the points. And remember, this time I'm looking at this second one, y2, okay? So got a lot of decimals here. Let's see, because the further to the right, the further I go, the better I am. This one has a 0.54. Well, that was the one I found that said that was my new most important point, right? I moved it to there. What else do I have? Well, I have 6, 5. So 6, 5 is right here. And then I've got 7, 7 is what it looks like. It's going up quickly, isn't it? I think I got that graphed right. And then after that, I think I'm going to be going, well, maybe 8, 11 is not on my chart. But what am I going to get close to? Well, this horizontal asymptote. So I'm going to draw it close to that. I'm going to let it rise quickly to the right. It's also an increasing graph, isn't it? And I've already put down that I know this horizontal asymptote is y is equal to 3. Now, what is the domain for this one? Well, the domain for my new one is going to be the same thing. It's going to go all the way to the left, and this is increasing, but it's also going to the right. So it's going to be a -infinity to a +infinity. And the range, Well, this time it is stopped by the horizontal asymptote at y is equal to 3. So I can say it stops at 3, but it goes all the way up to positive infinity. Well, that sort of helps me with that one. Let's draw another one. Now, this second graph is really a bit unusual because it's got 1/4 raised to the power of x, 1/4 to the x and plus 1, and we're not going to worry about the plus 1 right now, but what we really need to do is say, what is 1/4 raised to the power of x? What would that look like? Well, and I want you to keep this in mind. What I've got is, I could say 1/4 is really equal to 4 to the power of -1, isn't it? And then I can say, well, if 4 to the -1 were inserted instead of that 1/4, then I still have to raise that to the power of x, don't I? And if I do that, then what I've got is I multiply these two exponents. I have 4 to the -x. Okay, those are my extra notes for this. So I'm going to say this graph, they want me to graph, is really f of x equals 4 to the -x plus 1. Okay, that helps me because I want to figure out what my parent function is, and my parent function would be 4 to the positive x, wouldn't it? So I'm going to come down here and say, okay, I've got a parent function, and it would be, I'll call it p of x is equal to 4 to the positive x. It's not a really difficult one. It's going to be an increasing graph, isn't it? And it's going to have this point 0, 1 in it. And then it's going to have the point right here. It's going to be -1. And it's going to have 1 over b. So it'd be -1, 1/4. So I can figure out that's going to be a -1, 1/4 right about here, maybe. And then the next point I've got is going to be positive 1b, so it would be positive 1/4, right? So I kind of got 3 of the points. I know this one because I know my rules, and I could kind of graph this one. And I know that this is going to be the horizontal asymptote. It's going to be y is equal to 0. So I'm coming close to that. I'm going to go up, and I'm quickly going to rise to the right. And so I know it's an increasing function. I'll just go ahead and put that in. And I also know the horizontal asymptote has a couple of things, domain and range. Let's write those in. The domain of that one is going to be, of course, from -infinity on the left to positive on the right. The range, it's being stopped by y is equal to 0. And it never reaches it. But it does go all the way to positive infinity as far as up. Okay, so I've got my parent function fairly well identified here, and I'll just say this is p of x, okay, to keep from getting that messed up. That's going to be p of x. Now, let's go ahead and look at our other one. What does this tell us to do when the negative is up in the exponent? When the negative is a part of this exponent, when that negative has been added to the exponent, it says this is a y-axis reflection. And of course, the plus 1, you got that one, right? It's up 1. Now, when this one flips around the y-axis, it stops being an increasing function, and it's going to turn into a decreasing function, isn't it? It's going to go from being rise to the right to it's going to go down to the right, isn't it? So that would be a decreasing function. That's always what a y-axis reflection is going to do to us. Now, we could just go ahead and say, okay, I know it's going to have to go up 1. I'll put in my new horizontal asymptote. There it is. Y is equal to 1 this time. And I know these important points are going to, like this one's going to have to go up 1. And just because it flips around this axis, that point really shouldn't change too much, should it? So let's see what it says with our calculator as far as these points go. So I'm going to take my calculator, and I'm actually going to enter the parent function again as the blue function because I like to see the comparison of them. And you don't have to. You can just enter one function at a time if you'd like. But this one is going to be 4, and I'm going to raise it to the exponent of x. And that'll be on my color graphing calculator, that'll be the blue one. And then I'm going to go to the new function, and I'm going to say it's going to be a 4. And this time it's going to be raised to the power of, and I have to put the negative sign, not the minus sign in. It is a negative x. And then I get out of that, of course, and say it's going to have +1. Okay, see if I did that correctly. Let's look at the graphs. That one does increase going up to the right, and this one does decrease going down as it's going to the right. So it flipped. You can see the reflection around the y-axis. And the next thing you can see is that most important point that we always talk about, that 0, 1, looks like it just went up 1 and became 0, 2. That's because of the +1 at the end of my function here that was added. My transformation would take it that way. Let's look and see what the table tells us. I already have this one graphed, so I'm really interested in is these red y points. And I'll say, okay, that 0 went from 0, 1 to 0, 2. So here it is. It did just go up 1. And then as it goes positive, you can see it's really, really, really close to 1, doesn't it? Down here. In fact, it gets so close to 1 that the calculator doesn't know what to do with it. And so it just says it gets there, but we know it never reaches it. Okay? Now let's go the other way and see if we can get some points. -1, of course, is going to be -1, +5. There's one that we like. And then what else did I get? I need a -2 was 17, so I know it went really quick up there. And maybe I can do a +1, and it's going to be 1.25. So it really just moved up 1. There I am. So I can do it like this. And I'm going to try to show that it gets very close to that horizontal asymptote, but it never reaches it. Even if your calculator says that you get there, you know it never reaches it. The calculator, it gets so incredibly close, the calculator doesn't know how to handle it. Okay? All right. So what do we know about this one? Well, this one is a decreasing function. This one has a domain that is also still going to be -infinity to +infinity. But its range has changed, hasn't it? Its range is now being stopped on the bottom by 1, not 0, and it goes all the way up to +infinity. Now, let's talk about, on this page, some practical applications for all of these functions that have, exponents or exponential functions, okay, that have the unknown in the exponent. One of them is compound interest, and the other one is continuously compounding interest. So when we look at compound interest, we know that it can be accumulated a certain number of times per year or per period that we're looking at. Usually it's period per year. So we're going to be looking at some different things that fill into our formula for that. But for compounded interest, we've got this formula. It's the amount is equal to, and you're going to have to insert the P there. Just copy this formula. This one's correct down here. And so it's equal to P, the principal, times 1 plus the rate divided by the number of periods in that year. And that's raised to the exponent of those number of periods times the terms. And that's kind of a little bit confusing. We'll fill it all in just a minute. It makes a lot of sense when you're using it. Next, what about continuously compounding? Continuously compounding interest is where they developed the number E, that never-ending decimal E. And so we use that. We say principal times E raised to the power of rate times terms, okay? Or times time there. Now, let's look at this and say number of compounding periods per year. Just keep in mind, if they say semi-annually, it's got 2 a year. Quarterly is 4, monthly is 12. And think about if they said it was daily, it'd be 365. Now that's just so that we can figure out what N is in our compounding periods per year. If it's continuously compounding, we don't need the periods per year, okay? It's just happening continuously. So let's look at these and see if we can identify these parts. This says that 23,400 is invested. Well, that in either formula would be the principal, so that's going to be P. It's invested for 3 years, which is the time, and it's already in years, and that's what we need. And then it says it earns 8% interest. Now we have to put that's the rate, but the rate has to be put down as far as a decimal. So this is going to be 0.08. And I'll go ahead and say T is equal to 3. And then it says compounded quarterly. That's where we get N. And quarterly is, of course, there's 4 periods per year. And then they want to know what the accumulated amount is. In other words, not what the interest is, but what's the total amount once you have this. So we just enter it into our formula, and we say that's going to be A is equal to the principal of 23,400, and it's going to be times 1 plus, and the rate is going to be 0.08 divided by the number of quarters, the number of periods, which is quarterly, which is going to be 4. And then I'm going to raise it to an exponent. And the exponent is going to be n, which is 4, times 3, which is the number of years. Okay? So normally what I would tell you to do is go ahead and do this first and say that is equal to the number 12, right? So when you enter it in your calculator, you can enter it with parentheses, but you'll make fewer mistakes, and usually these aren't going to be terrible numbers anyway. So I've got that. Let me just go ahead and see what my calculator tells me the answer is. So I'm going to say 23,400, and then I say multiplied times 1 plus, and then I'm going to do division, which it will do the division inside the parentheses before it does that addition. So you're really okay. If you're not sure about something, you can always put it in parentheses, though. 0.08 and divided by 4. And I'll close the parentheses because then I'm going to raise this to the power of 12. Okay, and check it to see always if that looks right to you. Now, it will do this division before it does that addition, and that's what we wanted, okay? And then it'll raise it to that exponent, and then it'll multiply, so it has order of operations memorized. And I come up with the amount, 29,676.85. Let's just go to 2 decimal places since we're talking about money, and we'll say 0.86. So this amount is going to equal $29,676, and we'll say 86 cents. And that would be that would be our answer to our problem. Now let's do another one. We've got an amount that's invested for 7 years, and this time compounded continuously. So this is my principal right here. It's invested for 7 years. That's going to be time is equal to 7. And here's my rate. And when I say 5.7, I have to do that as a decimal, 0.057. And continuously gives me this formula that I need to use. So I'm going to say A is equal to the principal of 38,000 times E raised to the power of the rate times the time, right? So I'm going to say 0.057 times 7. Now, I'm going to just enter it into the calculator this way because those are some confusing numbers, but I'll be careful, and you be careful, make sure your calculator is doing what you think it is. So I got 38,000, and then I say E. Now, where did I find it? It's right above the division symbol, isn't it? Right over here. So I'm going to have to say second and division, and I entered E, and now I want to raise that E to a decimal. To an exponent. So I'm going to put my exponent in parentheses this time. I'm going to say 0.057 times 7. Okay, so it'll do that first before it does anything else, and I'm happy with that. And then I just hit enter. And I end up with the amount. It's going to be 56,632. And let's go to 68 cents since we'll round it to 2 since it is talking about money. And we've just got a couple more of these to do. On page 6, I'm going to skip this page because we've removed some material from this particular section, and so you really can skip over that page. On page 7, I've duplicated that one, so you can just cross that one out. We've already worked those 2 problems, and let's go on to page 8. We've only got a couple more examples of this that I wanted to work with you, and they are $1,000 invested for 10 years, earning 6% interest compounded continuously. So the first thing I'm going to do is write down my formula. My formula is A is equal to principal times E raised to the power of R times T. I look at it as the word PERT, okay? And it just kind of helps me to memorize that formula. So this is the amount is going to be equal to, and I'm going to identify everything in the problem. That's the principal. That is going to be the time. That is going to be the rate. And I have to say, I've got to fix the rate. I need the rate to be in the decimal, so I'll go ahead and say it's 0.06. and then it's compounded continuously. That's how I know that I have to use my E formula. So I'm going to have that PERT formula in there. Okay, so I've got $1,000. And I'm going to multiply that times E raised to the power of 0.06, the rate, times the time of 10. Well, and I could do that really pretty easy because this really is just kind of 0.6, isn't it? Makes it simpler, and I don't have to worry about parentheses as far as my exponents go. So let's say 1,000, and let's insert the number E, and then say it's raised to the power of 0.6. And I get the amount is going to be 1822, and we'll go to money again. We'll round it to 2 decimal places. Okay, next question. We have account 1 and account 2. They both start with an initial deposit of $10,000, and account 1 earns 5% compounded yearly, and account 2 earns 4.9% compounded continuously. So one of these is going to be our formula with compounded continuously, isn't it? And the other one is going to be compounded yearly. So we're going to use 2 different formulas with this one. So let's take a look at what this one is asking us to do. We've got account 1 and account 2. Both of them have an initial deposit of $10,000. So this is going to be the principal for 1 and the principal for problem number 2. Account 1 has 5% interest, so this is going to be the rate for 1 is equal to 0.05, and it's compounded yearly. So that's the time for number 1 is equal to, it's only going to be compounded once a year, okay? Now, account 2 has 4.9% interest, so that's going to be the rate for problem number 2 is going to be 4.9, which I'm going to say 0.049. And then compounded continuously says use E. And they want to know which one has the higher balance after 20 years. So I'm going to come over here with account 1. And I'm going to say A1 is equal to, and I'm going to have to write out my formula because I don't want to mess up my formula. I'm going to say principal times 1 plus rate divided by the number of periods times n to the power of t. Okay, so all I have to do is figure out what those values are, A1. I said the principal is the same for both of them. So it's $10,000, and it's times 1 plus. Now, the rate of this one for number 1 was 0.05, and the time here is going to be divided by 1. So really, I could just say 0.05, couldn't I? And what I'm going to raise it, the power I'm going to raise it to is the number of years, which this is going to be, isn't that going to be the, sorry, this is n. I'm trying to do this wrong. N that was 1, and then I'm going to raise it to the n, which is 1, times the time, which the time for both of them is 20, right? I think I got everything in place now. All right, so that's all I have to do. This is just kind of 1 times 20 is 20. This is going to be 0.05 divided by 1, which is just 0.05. Easy problem for my calculator. Let me clear this and say I have 10,000. Get the right number of zeros times 1 plus 0.05 over 1, which is just 0.05, and then I'm going to raise that to the power of 20. And what I came up with is amount 1 is going to equal 26,532, and I'll go to 98 cents, rounding to 2 decimal places. Okay, now let's take a look at the second one where we're going to compound this interest. Now that formula is equal to principal times E raised to the power of R times T. So I know the amount, I'll call this amount 2, is going to equal to that same $10,000 principal. And I know it has to be multiplied times E raised to the power of R, which is, this one is 0.049, isn't it? And times the same 20 years. And that's a little bit of a confusing exponent, so I'm going to be sure that I put that inside brackets, parentheses, okay? So I'm going to say 10,000 times E. Let me go ahead and put the E in. Whoops, I put pi in. Sorry. Let me clear this and start over again. Let's do e this time. And I'm going to raise that to the power of, and I'll put it in parentheses, 0.049 times 20. And check it and make sure I did this right, and then hit enter. And I get a different amount totally. So this one is going to equal $26,644.56 compounded continuously. Does a little bit better, doesn't it? Even though the rate was smaller. So that's kind of the end of this section that you're going to have to be familiar with. An exponential, it should help you with your homework when you have the exponential equations. And next time we'll be looking at logarithms.